everyone, welcome back to the IGCSE Physics Fast Your Walkthrough series brought to you by ZNotes. My name is Yumna, and while I'll be your host, we have an amazing contributor, Rushad, who will be guiding you through all the key concepts and questions for this past paper today. Together, we'll make sure you're well prepared and confident for your exams. Don't forget to hit subscribe so you don't miss any episodes, and let's get started and dive into this paper.
Okay, so yeah, let's start. This is summer 2023, paper 4-2, so theory. Yeah. So the first question asks, it shows a helicopter which is stationary at a height of 1500 meters above the ground. So part 1 says, state two conditions necessary for the helicopter to remain in equilibrium. So as we know, for anything to remain in equilibrium, basically it shouldn't be moving, right? So it needs to have no net force. I should just write it here. No net force. And it shouldn't be turning or spinning either. So no net moment. So yeah, these are the two conditions. Next up, it asks us, the mass of the helicopter is 3,200 kgs. Calculate the change in gravitational potential energy of the helicopter as it rises from the ground to 1500 meters. So as we know, GPE or gravitational potential energy is mg into delta h, which is change in height. Here it goes from the ground to 1500 meters, so change in height is 1500 into 9.8, or you can take it as 10 into 3200 kg, which is approximately 48 megajoules. So yeah, you can write that as 48,000 kilojoules, 48 megajoules, anything. Now, part B shows a vertical speed time graph for a parachutist who jumps from a stationary hot air balloon. The parachutist jumps from the balloon at time 0 and reaches the ground at B. The point A indicates when the parachute opens. On the figure, label a point on the graph where the acceleration is 0, negative, and decreasing. So, what is the acceleration? The acceleration is the change in speed. So here, since speed is on the y-axis, acceleration is basically the gradient, whereas the change in speed with respect to time and the gradient is change in the y value with respect to the x value. So basically, we need a point where the gradient is 0. That's where the graph is horizontal. And we can see that this part and this part, there's no change in speed. So acceleration is 0 here. Then we need a point where the acceleration is negative or where the gradient is negative. The only portion where the gradient is negative or the speed is decreasing is this part. So 2. That asks us where the acceleration is decreasing. So the speed isn't decreasing, but the acceleration is decreasing. That means the gradient of this graph is decreasing. So as you can see in this portion, the line, if this was a straight line, it should have gone like this. However, it curves downwards. That means the gradient or the steepness is decreasing. So the increase in speed is decreasing, thus acceleration is decreasing, and we can mark this area as 3. Next part asks that explain terms of forces, the changes in motion which occur from when the parachutist leaves the hot air balloon until point A. So, what happens until point A? Point A is when he just, just before he turns on the parachute. So the parachutist jumps from a plane. He has a downward force or weight acting downwards. So weight acts downwards. So there's a net force. So acceleration downwards. Okay. So then as he accelerates downwards, the resistive forces of the air or air resistance or drag starts to act in the opposite direction. So we can write drag force acts. And this drag force is directly proportional to the speed of the body. So as the person keeps accelerating and its speed keeps increases, drag force keeps increasing as speed increases. So as the drag force keeps increasing, eventually the drag force balances out the weight. So there is no net force, and hence a terminus velocity is reached because of no acceleration anymore. because no net force, so no acceleration. So this is the final velocity, the maximum speed, the terminal velocity. So yeah, that's the changes. So first we got the weight acting downwards, making it accelerate. Then drag force acting on the body, which increases as speed increases. Eventually, drag forces balance out, which give us this horizontal area. And then, yeah, so eventually he turns on the parachute. Okay, so next up is question 2. A student catches a cricket ball. The speed of the ball immediately before it is caught is 18 meter per second. The mass of the cricket ball is 160 gram. Calculate the kinetic energy stored in the ball immediately before it's caught. So we know that kinetic energy is equal to half mv square, which in this case is half into, it's going to be 0.16 because we have to convert it into kg SI units, into 18 square, which is uh, 25.92 or 26 joules. It takes 0.12 seconds to catch the ball and bring it to rest. Calculate the average force exerted on the ball. So as we know, force is equal to change in momentum by time, or mv by t. So here the original speed of the object was 18 meter per second. So the change will also be 18 meter per second to bring it to rest. So it's 0.16 into 18 divided by the time taken, which is 0.12 seconds. So this is going to be 24 newtons. As the student catches the ball, she moves her hand backwards. Affect the effect of this action on the student's hands. So you just seen here that force is equal to change in momentum by time. By moving her hands backwards, she basically increases the amount of time she interacts with the ball. So because change in momentum is fixed because it had original speed and we're bringing it to zero, as the time increases, the force decreases. So the force she needs to put on the ball, and as a result, the force she feels of the ball decreases. As the time increases, time taken increases. As a result, the force decreases. So it's less painful. Now, question 3 asks, it shows a person moving across an ice-covered pond to reach a ball on the ice. Explain why this way of moving across the ice is safer than walking. Use your understanding of pressure. So we know that pressure is equal to force by area. Here in this case, the force is basically the weight of the person. So the weight of the person is constant. Here it's unchanged. So compared to walking, here there's a greater area covering the ice. So as we said, force is constant because his weight is constant. Hence, because of the greater area, pressure is lesser than when walking. Hence, this is safer. Next question B asks us to, it shows the side view of the pond with a layer of ice floating freely on the water. The surface area of the pond is 5 meter square, mass is 690, density is 1000, point X is 0.45 meter below the ice. So we have all these values. Calculate the pressure at point X due to the ice and the water. Okay. So basically here we need, yeah, so we know that pressure is equal to H rho G of liquid. Okay. So here the height is 0.45, we know, but the density, so we know that density is equal to mass by volume. So volume is 5 in the area into height, which is 5 into 0.45, which is 2.25 is the volume meter cube. So since density is mass by volume, here the density is going to be 306.7 kg per meter cube. And so we have our density, we know acceleration due to gravity, we know height. So here pressure is equal to 0.45 into 306.7 into 9.8, which is 1352.4 Pascal. Question 4a asks us that the temperature of a fixed mass of gas at a constant volume is decreased. State and explain in terms of particles how the pressure of the gas changes. So we know that the volume is constant, mass is constant. The temperature is what is decreased. So we know that the temperature of the particles and their kinetic energy is directly proportional. So as the temperature decreases, the kinetic energy of the particles will decrease. And since kinetic energy is basically dependent on velocity, it means that the velocity of the particles will also decrease. Hence, they collide less frequently with uh, the walls of the container. So, since they collide less frequently, there's less of a change in momentum per time, so less force exerted, hence pressure decreases. Pressure decreases. Next question, we asked us to state the absolute value of 0 in degrees Celsius. So we know that absolute 0 refers to 0 Kelvin. And we know that to convert from Kelvin to Celsius, we have to subtract minus 273. Hence, absolute 0 is just minus 273 degrees Celsius. Explain what is meant by the term absolute 0. Refer to the particles in your answer. So you know that absolute 0 is the lowest possible temperature that can be achieved physically. So I already just mentioned that temperature and kinetic energy are directly proportional. So at absolute 0, lowest possible temperature also gives the minimum kinetic energy possible of the particles. Hence, they barely move, or they move like very, very slowly as soon as possible. Hence, the minimum velocity or no velocity is achieved by the particles of the gas. It's the temperature at which the it's the lowest temperature possible at which the particles have minimum to zero kinetic energy. Next question, she asks us that cylinder 1 contains 350 cm3 of gas at a pressure of 9 into 10 to the power 4. The gas is transferred to cylinder 2 and the pressure increases to something. The temperature remains constant. Calculate the volume of cylinder 2. So we know that PV, the quantity pressure into volume, is always constant. We also know that P1 V1 is equal to P2 V2. So for fixed mass of gas, pressure into volume is always constant. So hence, using this formula, we know that 9 into 10 to the power 4 into 350, since we're using the same units for both, the units don't matter in this case, is equal to 1.6 into 10 to the power 5 into, let's say, P for, or no, sorry, we're calculating volume, so V. So V is equal to this by 1.6 into 10 to the power 5 cm cube, which is 196.9 cm cube. So question 5 shows an electric heater, which is used to heat a room. The dimensions of this room are 4.5 into 6.1 into 2.4 meter cube. The density of the air is 1.2. Show that the mass of the air in this room is 79 kg. So as we discussed early on, density is equal to mass by volume. Hence, mass is equal to density into volume. Volume is equal to all these three dimensions multiplied with each other, which is going to be then 1.2 kg per meter cube into 4.5 into 6.1 into 2.4, which is 79.056 kg or 79 kg. So next up, the power of the heater is 1100 watts. The specific heat capacity of air is 1000 joule per kg per Celsius. Calculate the time taken to increase the temperature of the air in the room from 16 degrees Celsius to 20 degrees Celsius. So we know that we know the formula for in thermal energy, that energy taken to heat up a substance is equal to mc delta T, where m is the mass, c is the specific heat capacity, and delta T is the temperature change. So here the energy required to heat up all this air is 79, which is the mass, into 1000, which is the specific heat capacity given, into 4 degrees, because it's 20 degree minus 16 degree, that's the change in temperature, into 4, which is 306 kilojoules. So we know that energy is equal to power into time. So thus when we need to calculate the time taken, we just have to do energy divided by power. The power is 1100 watts. So it's going to be 316000 by 1100. So by doing that, we get 287.3 seconds. So that's the time taken to heat all of this, all of the air in the room. Question 3 asks to suggest one reason why the time calculated in A2 is the minimum time needed to increase the temperature of the air in the room from 16 to 20 degrees Celsius. Now, whenever it asks about the minimum time, this is a very regular question. It's basically because either the heater is not 100% efficient, or but which is normally not the case for heaters. So here we have to say that the heat is not just used for the air. It could be used for surrounding objects. It could be absorbed by the walls. So we say that the heat is absorbed by the walls of the room. Hence, since some of the heat goes to the walls, you need more heat than this to actually heat the room by 4 degrees. So that's why the time we calculated is the minimum time. We're assuming no heat loss happens. Question B asks us, it shows a cross section of a double glazed window in the room. State the main methods of thermal energy transfer from the room to outside, which are reduced by this type of window. So this window has an outer glass pane and a narrow air gap. So there must be air in this. It's not a vacuum, however. But even if it's not a vacuum, but it's air, conduction reduces severely, because conduction is best in solids, slightly existent in liquids, and basically non-existent in gases. Because in gases, the particles are so far apart, and we know that conduction uh, is when particles vibrate and collide with neighboring particles to spread heat energy. That's why conduction normally doesn't happen in gases. Hence, by having a narrow air gap here, conduction is the one of the types of transfers which is completely reduced. Next, the second one, which is also reduced, is actually convection. You might be thinking that this is an air gap, so convection takes place in fluids, which is also air. So why will convection reduce? The thing is, the question is asking us thermal energy transfer from the room to the outside. So let's say that this is the room and this is the outside. So if these yeah, because of the ceiling, which is shown by these bricks, when these air particles get the thermal energy, they can do convection, but they'll just transfer the heat energy among themselves in this column. They have no way of physically transferring the energy outside the room, because, as I said, they can't do conduction. So hence convection, and because the top is closed, convection cannot allow heat energy to escape this room. So that's why convection is another thing that goes down because of this arrangement. Radiation doesn't go down because, as we know, radiation is just the travel of heat through a vacuum. So heat that's radiated could still leave this air gap and the glass panes and escape. Hence, the two methods which are reduced are conduction and convection. Now, the two types of seismic waves are the P waves and the S waves. State the types of wave that P waves and S waves can be modeled as. So this we just have to know. There's really not much to uh, explain in this. So we know there's two types of waves: longitudinal and transverse. So longitudinal waves are basically those where if they're moving this side, the particles vibrate towards the direction of motion. So there's rarefactions, compressions. Whereas transverse waves are basically transverse waves are basically when it's moving like this, the particles travel like this, like this, like this, like this. They vibrate like this while moving here. So P waves are longitudinal, and S waves are transverse. So the velocity of a P wave in the Earth's crust is 72 km per second and its frequency is 4.5 hertz. Calculate the wavelength of this P wave. So as we know that velocity of a wave is the wavelength into the frequency. Hence the wavelength is equal to velocity by frequency, which is 7.2 kilometer by 4.5, which is 1.6 kilometers. So that's the wavelength, or 1600 meters. You can write it as both. Now, question 7 shows a container of oil. A ray of light shines on the surface of the oil. The refractive index is 1.47. On figure 7.1, draw the normal to the point where the ray enters the oil. As we know in any light diagrams or questions, a normal is basically a perpendicular drawn to the surface on which a light of ray falls. So here to this oil surface, the normal will be a straight line like this, perpendicular to the oil. So yeah, this is a very rough sketch, but this is what it's supposed to be. Question B asks us that the angle x is 56. Now calculate the value of the angle of refraction. We know that the refractive index is equal to sine of angle I, which is the angle of incidence, by sine of angle R, which is the angle of refraction. Here, we know that the refractive index is 1.47. The angle of incidence is this angle between the incident ray and the normal. So this angle, we know that this as a whole is a right angle. So we know that the angle of incidence I is basically 90 minus x. We've been given the value of x in this question, which is 56. So 90 minus 56 is 34. So the angle of incidence is 34. Hence, sine r is equal to sine 34 by 1.47. Is it 1.47? Yeah, it's 1.47. So sine 34 by 1.47 is 0.38. So sine inverse that answer gives us 22.4 degrees for the angle of refraction. State the approximate speed of light in air. This we know, it's 3 into 10 to the power 8 meter per second. Nothing complicated here. Calculate the speed of light in the oil. Give your answer to 3 significant figures. So we need this information for this question. So as we know, refractive index is sine I by sine r, but refractive index is also speed in vacuum or air, which is roughly the same thing, by speed in the medium, which in this case is oil. Hence, the speed in oil is speed in vacuum divided by refractive index, which is 3 into 10 to the power 8 meter per second divided by 1.47, which is 2.04 into 10 to the power 8 meter per second. Question 8 asks us, state what is meant by magnetic field. A magnetic field is a region where a magnetic pole experiences a force. Define the direction of a magnetic field. So as we know, if this is a bar magnet, north, south, we know that opposites attract, and we know that a magnetic field always comes from the north side and towards the south side. So we see that a magnetic field direction is towards the south pole, and we know that the north pole would be attracted towards the south pole. So how we say it as is that the direction of a magnetic field is the direction of force experienced by a north pole of a magnet. Question B asks us, it shows a negatively charged metal sphere. Draw 4 lines to show the electric field and its direction. Electric fields are similar to magnetic fields. Electric fields go from positive charges to negative charges. So since these are negative charges, electric field lines will be drawn towards them. So we can just draw 4 lines here. And it's very important that the lines touch the sphere. There's one mark for that. That's most important. They must be touching the sphere. Question C shows a circuit. The three cells are identical and have zero resistance. The resistors R1, R2, and R3 are identical. The reading on the voltmeter is 6 volt. So this whole battery has an EMF or potential difference of 6 volt. When the diode is conducting, it has zero resistance and zero potential difference across it. Okay. Determine the EMF of one cell. So we know that the EMF of this whole section is 6 volts. The three cells are identical. So of course, the EMF of one cell is 6 divided by 3, which is 2 volts. Now determine the ratio of the potential difference across R2 to the potential difference across R3. Now, so because these two are parallel, R1 and R2, the potential difference they get is the same. So these can be thought of as one single entity. So basically R3 and both of these combined are competing in series for the potential difference. We can think of it like that. Let's just think of it as a circuit like this with a voltmeter connected to the battery. Um, 1 second. Yeah, where this is R3 and this is R1 and R2. So in a circuit like this, so we need to find the combined resistance of R1 and R2. So let's just take that as X, okay? So we know in parallel, the sum of resistance is basically, so 1 by X plus 1 by X is equal to 1 by the combined resistance. So 2 by X is equal to 1 by R. So R is equal to X by 2. So that means basically the effective resistance is half of the resistance of each of the resistors. So given that R3 is identical to R1 and R2, the resistance of R3 is also X. So in this imaginary circuit, if we have R3 here, its resistance would be X and its resistance would be half X, the combined of R1 and R2. So, the potential difference of the cells would be divided based on the ratio of resistance. So since the resistance of R3 is double of R2, so here we can see the resistance of R2 is to R3, the ratio will be half is to 1, or we can just write it as 2 is to 4, 1 is to 2. Yeah, half is to 1 is the same as 1 is to 2. So yeah. Now all the cells are reversed. State and explain the change in current in R1. So we know that in a cell, the longer stick is positive and the shorter one is negative. And we also know that current moves from the positive through the circuit to the negative side. So if the cells are flipped, that means instead of going like this, the current will now go like this. So when it goes here, it meets a diode. So the diode prevents current flowing this side. Hence, it doesn't go this side, it just goes like this and back into the cells. Hence, R1 does not get any current. So we can basically say no current in R1 because the diode doesn't allow current flow in that direction. Determine the new value of the ratio of PD across R2 to the PD across R3. So now that R1 is basically out of the picture, this is just a simple series circuit because there's no R1. And since we know both R2 and R3 have the same resistance, it's basically just 1:1 because they have the same resistance. Uh, there's a fixed EMF of the battery, so it's just going to be divided equally since same resistance. So it's just 1:1. Now, question 9a, the table shows some properties and values for alpha particles, beta particles, and gamma radiation. Complete the table. So we know that alpha particles are basically two protons and two neutrons. They're the same as a helium atom, which has a mass number of 4, atomic number of 2. So that's 2 plus 2, 2 protons, 2 neutrons. So we have two neutrons here. A beta particle is just an electron. So the number of protons is 0. And the charge, since here two protons give a charge of 3.2 into 10 to the power minus 19, one proton would give just half of it, which is 1.6 into 10 to the power minus 19. And since electrons have negative charge, it will be minus 1.6 into 10 to the power minus 19. Now, gamma radiation, we know it's not there's no particles involved. It's just ultraviolet radiation. So there are no particles, no neutrons, no protons. And since no protons, electrons, so zero charge as well. And it's stopped by, heavy amounts of like a good length of like thick lead or even thicker concrete. Yeah, if it's concrete, it needs a greater thickness than if it's lead to stop it. State how beta decay changes the nucleus of an atom. So as we know that in beta decay, a neutron from inside the nucleus basically splits into one proton and one electron. It just splits into a proton and electron. So how it changes the nucleus of an atom, since electrons are outside the nucleus, we can ignore this. Basically, one neutron turns into a proton. So neutron uh, neutrons are one less than before, and protons are one more than before. So one less neutron, one more proton. Next, it asks us that a radioactive detector used in a laboratory detects a background count rate of 30 counts per minute. A radioactive source is placed in front of the radiation detector. The initial reading on the detector is 550 counts per minute. The half-life of this source is 25 minutes. Calculate the expected reading on the detector after 75 minutes. So we need to find the corrected count rate, which is basically 550 minus 30 equal to 520. So we have our actual count rate, which is 520. So we also know that basically there's a formula for count rate after a certain amount of time, which is original count rate, which in this case is 520, divided by 2 to the power x, where x is the number of half-lives. The number of half-lives is basically time taken, which is 75 minutes, divided by the actual half-life, which is 25, which is 3. So the number of half-lives in this case is 3. So it's basically 520 divided by 8, which is the count rate after 75 minutes, because basically the count rate has halved thrice. So we can also just divide it by 2 3 times, which is 65. So now the actual count rate by the substance is 65. However, the question is very specific. It asks us the expected reading on the detector. So we know that on the detector, it'll show a background count rate of 30 counts per minute. So the reading on the detector will be 65 plus 30, which is going to be 95 counts per minute. State two safety precautions taken when moving, using or storing radioactive sources in a laboratory. So there's many, as we know. One is either you maintain a safe distance from the source, stay as far as possible, and the other is you cover the source in lead lined boxes. Others are that like monitor your time of exposure, keep track records, stay in a different room, and wear lead line suits, wear gloves, etc. But these two should be enough. Now, the final question, question 10a, asks us, state the equation that defines average orbital speed v of a planet. State the meaning of any symbols you use. So normally, we know that speed is equal to distance by time. So for a planet, the orbital speed, let's say this is the sun around which it's orbiting, and this is the orbit. It's not typically a circle, it's an ellipse, but for approximation, we think of it as a circle. The distance in this case is basically the circumference of the circle, which is 2 pi r, where r is the distance from the the sun or the source, or it's the orbital radius, we can say. So here it's r, which is orbital radius. So distance is 2 pi r by capital T, which is the time period of it's the orbital time period. So for example, for Earth, it's 365.25 days. That's how much time it takes for a year to happen. So we can say orbital speed v is equal to 2 pi r by t, where r is the orbital radius and t is the orbital time period. Suggest why countries that are a significant distance from the equator experience significant temperature variation throughout the year. So countries that are a significant distance from the equator, so if they're like this and there's the sun lights, so as the sun earth keeps moving, we know that its orbit is elliptical. So at some points it's closer to the sun and at some points it's further. So when it's at the center, it really doesn't matter how close or far it is from the sun. But when it's at the edges, when the sun's rays hit it at an angle, how far or how close it is makes a difference. Since here it's harder, when it's closer, it's harder to hit an angle than when it's further. So when it's a significant distance, the sun rays hit at different angles throughout the year. Hence, there's significant temperature variation. Now, question C asks us to fill in the gaps about a star much more massive than the sun. So here, the sun is normally a small star, if you guys don't know. So we're not talking about the sun, we're talking about much bigger stars than the sun. So, that's what you need to remember as which case, since there's obviously two paths, stars smaller than the sun, stars smaller like the suns, and bigger than the sun. So the stage that follows the stable state in the life cycle of the star is, in this case, it's going to be the red supergiant stage. The red giant stage, what our sun is like touted to have in some thousands and billions of years, is for a star small like the sun. This is about a star much more massive than the sun. So this will be the red supergiant stage, not the red giant. Next, it then explodes as a supernova to form a nebula. So after it's ran out of energy in itself and ran out of all the elements to combine and create nuclear fusion and form energy, it then explodes one last time as a supernova, forms a nebula, and then this leaves behind two things depending on the size of the star: either a neutron star or a black hole if the star is much bigger. So either a neutron star or a black hole. The last part asks us that a galaxy is moving away from the Earth with a speed of 33,000 km per second. The value of the Hubble constant is 2.2 into 10 to the power minus 18 per second. Calculate the distance from the galaxy to the Earth. Give your answer in light years. So we know that the Hubble constant is equal to speed by distance. Speed a galaxy is moving away from the earth and the distance it is from the earth, and we know this is constant because of various experiments. We've created the Hubble constant that the faster they move away from us, the farther they are from us. So to calculate the distance, we basically just have to do distance is equal to speed by the Hubble constant. So here speed is 33,000 kilometer per second, and this is 2.2 into 10 to power minus 18 per second. So the per second cancels out. 33000 by 2.2 uh, into 10 to power 18 is basically 1.5 into 10 to power 22. uh, Sorry, it's 1.5 into 10 to the power 22 kilometers. So we know that 1 light year is basically the amount of time it takes for the amount of distance light travels in a year, which is, distance equal to speed in time, which is 3 into 10 to power 8 into, that's the speed per second. So into 60 seconds, into 60 seconds for an hour, into 24, into 365. So 9.46 into 10 to power minus 10 to power 15 is 1 light year. So we have this, which is 1.5 to 10 to the power 22 kilometers. We will multiply this by 1,000 to get meters. And then we'll divide this by the answer we have of the amount of 1 light year, which is 1.6 into 10 to the power 9 light years. So the distance is 1.6 into 10 to the power 9 light years. So yeah, that's all for this paper, and that's all from my side. So yeah.
All right. Okay. That wraps up today's episode. We hope you found it helpful and feel more confident about tackling past papers. We've got plenty more episodes coming your way, so don't forget to subscribe and hit the notification bell to stay updated. Thanks for watching, and we'll see you in the next episode.